This is a problem that asks about the angular momentum of various elements in the solar system. Specifically, the problem asks us to find a fraction that represents how much of the solar system's total angular momentum is taken up by the angular momentum of the planets. So the problem is basically asking us to find a ratio of the angular momentum of the planets to the angular momentum of the planets plus the angular momentum of the sun. So this is the solar system's total angular momentum, this is just the planets, and that's the ratio we want to find. And we're going to estimate that ratio using a sample of just 4 of the planets here. So that's what we're going to do. So I'm going to go over a few basic equations we'll need to use. First off, the angular momentum of a body is equal to its moment of inertia, I, times its angular velocity, L. And we're not given angular velocity for anything in this problem, but that's not too bad because we have a formula for angular velocity telling us that it's equal to 2 pi times its period. So for the planets, that's going to be its orbital period, which is given to us in this table. And for the sun, that'll just be its period of spin, which is given to us as 25 days. So let's do that first. Let's first find the angular momentum of the sun. So as we mentioned earlier, it's equal to the moment of inertia times its angular velocity. Now if you look up what the moment of inertia of a sphere is, which is what we're going to assume the sun is, then the moment of inertia of a sphere is equal to about 2/5 times the mass of the sun in this case, times the square of the radius. So the radius of the sun squared. And we are given, in the problem, we're given the mass of the sun and we're given the radius of the sun. So we've got that part covered. And times 2 pi times the sun's period of spin, which is given as 25 days. So we'll want to convert that into units we can work with. So if you look up the conversion rate for 1 day to a number of seconds, or if you just do the math with the calculator, then 1 day is equal to about 86,400 seconds. So we'll just use this as a little chain link conversion type deal. And if we put that into our calculator, then we find that the sun has an angular momentum of about 1.1217 times 10 to the power of 42 kilogram meters per second. That's a pretty big number. But now let's try finding the angular momentum of the planets, of the other planets we're dealing with, and see what we can do there. So first off, the angular momentum for Jupiter. Again, it's the moment of inertia times the angular velocity. Now we're not going to use this same formula for the angular momentum, or for the moment of inertia, I mean, because this only applies for a sphere. But if we're looking at a planet, one single planet revolving around the sun, then we can approximate this system by treating the planets as a particle in this rotating around this system. So for the moment of inertia here, I'm just going to use the standard moment of inertia formula for a particle, just mr squared. That is equal to the mass of Jupiter times the radius of Jupiter squared, or the radius of the Jupiter's orbital radius. And then we multiply that by 2 pi over t, or it's 2 pi divided by the period of Jupiter's orbit, which is given to us in the little table. See, we just need the mass of the planet, the radius, like the orbital radius of the planet, also known as its mean distance from the sun, and its orbital period. So all that information is just given to us in the table. So if we put in the numbers for Jupiter, for example, then we find an angular momentum of about 1.9240 times 10 to the power of 43 kilogram meters per second. So that's the angular momentum of Jupiter. So what we did for Jupiter, we can basically just repeat for the other 3 planets, Saturn, Uranus, and Neptune, using the data given to us in this table. So just go through that, put in this basic formula, mr squared times 2 pi over t, and put in the numbers for all 4 planets, and then we'll have everything we need to take this final ratio and get the final answer to the problem. So what we end up finding is that the fraction f is equal to, and then in the top we'll have the sum of the angular momentums for the planets. So for Jupiter, that's about 1.9240 times 10 to the power of 43, and then so on and so forth, and just keep adding what you get for the angular momentums of all the others. And then in the bottom half of the ratio, you do that exact same thing, except at the very end of it, add the angular momentum that we found for the Sun, about 1.122 times 10 to the power of 42. And putting all this into our calculator, we find a ratio of about 0.965. So that's a pretty high ratio. That is, and that kind of gets the point across, that most of the angular momentum contained in the solar system is within the planets. So this is the final ratio that is the answer to this problem. So that's all for this video. I hope it helped you out. If it did, please consider subscribing, as that'll help me out make more videos like this. And if you have any questions, leave a comment down below. If you'd like to make a request for a future video, or if you just want to hang out, I have a Discord server linked down below, as well as my Twitch. So both of those you may check out if you'd like. But that's all for now, and I hope you have a lovely day. Bye-bye.